Hello and welcome back. We are to a new convergence divergence test. There's actually two of them. These are called the comparison tests. And what we're going to do is we're going to compare our current summation to another summation. First of all, we need to make sure that it's a good comparison. And if it is a good comparison, then what's going to happen is if our comparison series is convergent and all of the terms of our original series are less than our new series for all n, then this one will also be convergent. Meaning, and this is what's called the direct comparison test. And then meaning we're directly comparing the terms themselves. And this one, again, B is going to be our chosen that we're going to choose to compare it to. And it'll make more sense when I get to an example down here. But if this one's divergent and all of the original terms are bigger than or equal to our new terms, then this one's also divergent. So this one tests for convergence and divergence. Now, what makes this one, I'll just say my least favorite test is that it has to follow this or this. And let's say this one's convergent and it's not that case. Well, all that means is we can't use this test. This test is not good enough for us. We need another test. And that happens. All right, let's jump into it with our example one. And so we're going to determine whether this is convergent or divergent. And I need to figure out what to compare it to. And I'm going to, in almost all these cases, just truncate it like this. I'm just going to block off this, and I'm going to make my new one 5 over 2n squared. So here's my b sub n. It's going to be 5 over 2n squared. And I know that for these, this will always be less than this. Now, how do I know that? I know that because when I'm adding numbers in the denominator like that, this means that this denominator will always be larger than that denominator, which means this overall fraction is always going to be smaller than this one here. And when I said I didn't care for this test all that much, if that was minus 4n, then it's kind of weird. We don't know that it's always going to be less than, so we wouldn't be able to use this test. But in this case, we've clearly demonstrated that that happens. Something else, we also know that this, which is based on this, is convergent. I know that's convergent because it's a p-series, right? P is bigger than 1 in this case. Convergent by p-series. So now we know that what we're comparing it to is convergent, and all of our a sub n terms are less than or equal to this for all n. And so our conclusion is that this is also convergent. By the direct comparison test. Let's do another one. So here we have summation of 1 over n cubed plus 8. Now, again, I'm just going to truncate that, and I'm going to compare to b sub n in this case, which is going to be 1 over n cubed. And we know, once again, is a p-series, so this one's convergent. And we know that 1 over n cubed plus 8 is going to be less than or equal to 1 over n cubed for the same reason as this one. I'm adding in the denominator, so this denominator will always be larger than this denominator. Therefore, the overall fraction will always be smaller. So we have convergent, what we're comparing it to. It's always less than, therefore, also convergent. All right. So for this next two, what am I going to compare this to? Well, I'm going to know that the largest that cosine can get is 1. That's the biggest that that function can ever get. Otherwise, it's always going to be something less than 1. So I'm going to compare to this here. Because then, for sure, this will always be less than or equal to a rate to the n. And this becomes this here. This is a geometric series. And R in this case is 1 over E, which is definitely less than 1. So it's convergent. So we have what we're comparing it to is convergent. It's always going to be the original function, this here, a sub n, is always going to be less than our b sub n. Therefore, our original is convergent. Now, once again, we don't know what it converges to, and that's okay. We don't need to know that. We just need to know that it converges. When I say we don't need to know what it converges to, later in later sections, we will actually be creating these to mimic something else intentionally. All right, let's try 4. Now, I'm going to compare to b sub n is 1 over n. Now, I also know that this is divergent. It's actually called a harmonic series. But we know that it's divergent because of, well, actually, for several reasons. We could do the integral test, and that integral will go off to infinity, so it's divergent. We could also do the p-series test. To be convergent, it has to be strictly bigger than 1. In this case, the exponent here is just 1. So this one's definitely divergent. And also, I want to point out that our a sub n, which is ln of n over n, that this will always be bigger than 1 over n. And you can see that that numerator is going off to infinity, so it's always going to be bigger than that 1 there. And because it's divergent and our original is larger than all of the terms of our comparison, therefore, n equals 1 to infinity, ln of n over n is divergent. So that is the direct comparison test. And what we're going to do next is a different type of comparison test called the limit comparison test. This one I do like. This one to me is much more useful. So we have our original, that's the a sub n, and then what we're comparing it to, and we're going to do something very similar to what we were just doing to do the comparison. And we're going to assume that all the terms are positive. If we take the limit as n goes to infinity of a sub n over b sub n, and that converges to a specific positive number, then both of them converge or both diverge. So similar to the other comparison test, but this time we're running a limit. And this one, again, we get a lot more flexibility with compared to the other one. All right, so what we're going to do to find our b sub n term is the same thing. I'm going to truncate. I'm just going to make it that, and that's what I'm going to compare it to. So here's my a sub n. this right here. So my b sub n in this case is going to be 1 over 2 to the n. And by the way, summation of 1 over 2 to the n converges. It's a geometric series. R is 1/2 in that case. So what we're comparing it to is convergent. So if we can run this limit and we get a specific number, and by the way, this specific number, we're going to design our problem so that that limit L is always going to go to 1. So I'm going to take the limit as n goes to infinity, a sub n, which is 1 over 2 to the n minus 1 over 1 over 2 to the n. Let's fix that. This is going to be 2 to the n over 2 to the n minus 1. And can you see that as n gets really, 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 really large, that minus 1 becomes super irrelevant? Meaning this limit and all the limits like this, when they're alike like that, are all going to go to 1 if we design them the same way. Therefore, because we know this one converges, all this part does is tell us that what we're comparing it to is a good comparison. And again, that's because this one converges, our limit goes to a specific positive number, good to go. All right, let's try number 6 here. For this one, I'm going to compare my b sub n is going to be without the plus 1. And can you see that the ends are going to reduce? I'm going to actually compare it to that, and I'll show you why here in just a second. But we know that when we do drop those ends and we get 1 over n, square root of n is to the 1/2, that diverges because this is a p series and p is 1/2, which is less than 1. So what we're going to compare this one to is divergent. But as I write this out, and right off the bat, I'm going to do this. I'm not going to write that divided by that. I'm just going to take the reciprocal of that. That's going to make it a whole lot easier. So we have n plus 1 over n root n times n root n over n. And I'm hoping that we can see, well, first of all, these completely reduce out. We end up with n plus 1 over n. And again, because the exponents on these are the same, this limit will exactly go to 1. Now, it's easy to mix this up here and say, oh, the limit exists, therefore it's convergent. No, all that means is what I was comparing it to is going to have the same fate. So in this case, this means therefore our original n plus 1 over n root n is divergent because what I compared it to was divergent. All right, example 7. Okay, so what to compare this one to? This one's getting a little funky here. I'm going to truncate that, and I'm going to truncate that without the plus 5. Now, what that's going to give us, or b sub n, is going to be 2n squared over n to the 5/2 power. Now, that may look weird, but all I did was take n to the 5th, and because of the radical, I made it the 1/2. And let's see what this one actually does. When I reduce that, we end up with, well, 2 on the outside. We end up with 1 over n to the 1/2 power, which is divergent by p series, right? P is less than 1, so that's divergent. And so let's run our limit once again. So limit of 2 to the n squared plus 3 to the n over times, then I'm going to do the reciprocal of this one here. And this limit, believe it or not, has the exact same exponents. You can see that those are the same, and that plus 5 becomes irrelevant when n is 50 trillion, right? We're going up to infinity here. And you can see that plus 3n becomes irrelevant there. So all of our lead coefficients are the same. This limit exactly goes to 1. Therefore, summation n equals 1 to infinity squared plus 3n is also divergent, right? What I compared it to. All right. 2 more examples here. All right, so what am I going to compare this one to? No problem. Again, just chop up that 3. So b sub n is 9 to the n over 10 to the n. And our summation becomes 9/10 to the n power. Now, this is a geometric series. And r in this case is 9/10, which is less than 1. So this converges. So if this is a good comparison, then our original will be convergent. And once again, we've designed these so that our limit times the reciprocal. That limit, again, is exactly go to 1. So you can see 9 to the n, 10 to the n, 9 to the n, 10 to the n. That plus 3, when n is super, super big, becomes irrelevant. And the whole thing converges exactly to 1. Therefore, to the n over 3 plus 10 to the n converges by the limit comparison test. All right, this one is going to get a little even more weird. This next one. All right, so I'm going to compare it to, once again, I'm going to truncate it. Compared to b sub n is going to be cubed root of n over the square root of n to the 3rd. Let's rewrite that a little. All right, so let's see what we even have here. So I have 1/3 minus 3/2, convert to a fraction. It's going to be negative, obviously. So this leaves me with n to the 7/6. Now that's going to give me this here, and this is a p series again. So we're ending up with, here's a p series, where p is 7/6, which is bigger than 1, which makes it divergent. So this one's divergent. I'm sorry, convergent. It's bigger than 1, convergent. So we're going to end up with our limit again. Times the reciprocal of that. And you can see when I multiply that times that, that's going to be the same. Which means that limit, once again, exactly goes to 1. Making this also convergent. Not too bad. Now we have our last one here. All right, so what are we going to compare this one to? Well, I'm going to get rid of that -2, and we are going to compare this to b sub n is going to be 4 to the n plus 1 over 3 to the n. Now we got to, when we do the summation, so the 4 to the n plus 1 is actually 4 to the n times 4. So I'm going to pull an extra 4 out. So we end up with 4 to the n over 3 to the n. And this is a geometric series where r in this case is 4/3, which is bigger than 1, which makes it divergent. So when we run our limit, over times 3 to the n or 4 to the n plus 1. Actually, very nicely with this one, those reduce out completely. And you can see we have 3 to the n over 3 to the n. Because that -2 out at infinity will become irrelevant, that limit goes to 1. So it's a good comparison. And our conclusion is that our series is divergent. And those are the comparison tests.